Welcome to our lesson on exponential models. Exponential functions are incredibly important in mathematics because they model many real-world phenomena, from population growth to radioactive decay. Today, we'll learn how to solve problems involving exponential growth and decay by working through two step-by-step examples. Before diving into our examples, let's understand the general form of an exponential model. An exponential model has the form p of t equals p sub 0 times b raised to the t power. Here, p of t represents the quantity after t time units, p sub 0 is the initial quantity, and b is the base or growth factor per time unit. If b is greater than 1, we have exponential growth. The quantity increases over time. If b is between 0 and 1, we have exponential decay. The quantity decreases over time. Now let's solve our first example, which involves exponential growth. Example 1. A certain bacteria culture doubles every 3 hours. If you start with 500 bacteria, how many bacteria will you have after 12 hours? Let's solve this step by step. Step 1. Write the exponential model. We know that our model has the form p of t equals p sub 0 times b to the t. We're given that p sub 0, our initial population, is 500 bacteria. We're also told that the population doubles every 3 hours. This means that b to the power of 3 equals 2. Solving for b, we get b equals 2 to the power of 1/3, or the cube root of 2. Thus, our model is p of t equals 500 times 2 to the power of t over 3. Or, equivalently, p of t equals 500 times the cube root of 2 to the power of t. Step 2. Compute p of 12. Now we can substitute t equals 12 hours into our model. P of 12 equals 500 times 2 to the power of 12 over 3. This simplifies to 500 times 2 to the power of 4, which equals 500 times 16. So after 12 hours, we'll have 8,000 bacteria. Let's visualize this exponential growth. Now, let's move on to our second example, which involves exponential decay. Example 2. A radioactive substance has a half-life of 5 days. If you start with 200 grams, how much remains after 8 days? Let's solve this step by step. Step 1. Write the decay model. An exponential decay model also has the form a of t equals a sub 0 times b to the t, but now b is between 0 and 1. We're given that a sub 0, our initial amount, is 200 grams. Half-life 5 days means every 5 days the amount halves. So b to the power of 5 equals 1/2. Solving for b, we get b equals 1/2 to the power of 1/5. Thus, our model is a of t equals 200 times 1/2 to the power of t over 5. Step 2. Compute a of 8. Now, we can substitute t equals 8 days into our model. A of 8 equals 200 times 1/2 to the power of 8 over 5. This can be rewritten as 200 times 2 to the power of negative 8 over 5. Numerically, 2 to the power of negative 8 over 5 is approximately 0.33. So a of 8 is approximately 200 times 0.33, which equals 66 grams. Therefore, after 8 days, about 66 grams of the substance remain. Let's visualize this exponential decay. Let's summarize the key steps to solve any exponential model problem. Step 1. Identify the initial amount and rate information, such as doubling time or half-life. Step 2. Determine the base b. If the quantity changes by a factor k in t time units, then b equals k to the power of 1 over t. Step 3. Write the model as p of t equals p sub 0 times b to the t. Step 4. Plug in the desired time t and compute the result. Let's compare growth and decay side by side to see the difference in their behavior. Exponential models are powerful tools for describing many real-world phenomena. Exponential growth models apply to population growth, compound interest, and viral spread. Exponential decay models apply to radioactive decay, depreciation of assets, and cooling of objects. By following the steps we've outlined today, you'll be able to solve any exponential model problem that comes your way. Thank you for watching.